In this video, we're going to look at parabolas and how certain parts of the equation can influence where that vertex is and where the parabola opens up from. In a previous video, we looked at the value of a, the coefficient of the x squared, and how it will influence the width of the parabola and whether the parabola opens up or down. So a little reminder, if a is positive, we generally have the parabola opening up. In fact, we always have the parabola opening up. If a is negative, it's going to open down. The three parabolas here on the right are all opening up, so A is positive in each case. What we have here is a situation showing how the value of A, not just its sign, can influence the width. This red equation in the middle is actually just y equals x squared. The blue graph that is thinner actually has a higher value of A, has a value of 2x squared. As the value of A gets higher, what it does is it stretches the height of the parabola, and that makes it look like it gets narrower. So the width appears to get narrower. The green graph on the outside actually has an A value of 1/4. As your A value goes down from 1 towards 0, it's going to widen the parabola because in essence it's shrinking the height. So the A value involves whether it tells you whether the parabola opens up or down and the width of the parabola. What we're going to look at in this video, though, is how we shift a parabola from side to side or up and down. All right? Let's use Desmos to investigate how adding or subtracting a number in the equation of a parabola affects the graph. Let's start with the basic graph of a parabola, just the very basic y equals x squared, graphed in this case with green on our grid. Now let's adjust that by adding to the outside of x squared a constant. So for instance, let's say we have y equals x squared and we add 3. Notice my new graph has a vertex that is now at 0, 3, compared to where it was originally at the origin. So my original graph had a vertex that at the origin and opened up from there. My new graph, where I added 3 on, shifted everything up 3. If I instead had subtracted a number, subtracted 4, my new black graph, notice, is the same basic shape but shifted down so that the vertex is at 0, -4. Now Desmos has this really cool thing you can do. It's called using a slider. And how you use a slider is, let's say we want to investigate this entire situation for anything you might add on. So I might say plus, and let's say any number k. And notice as soon as I put in k, it says add a slider, and I'm going to click on that k blue box. And when I do that, it gives me a slider of values of k. It starts me off at k equals 1. Well, look at where my red graph is. It's right here, and my vertex is at 0, 1. If I move my slider around, notice it goes up, and here as I have it at k equals 3 plus 2, notice it's slightly above where my y equals k plus 3 is. And as I increase the value of k with the slider, you can see the graph goes up. Or as I decrease, it goes back down. If I make it be 0, see if I can get that, then I'm right overlapping the original y equals x squared graph. If I make it negative, the graph continues to go down. And in fact, you can hit the play button on this slider, and it will play back and forth and show you that really adding a constant to the outside of y equals x squared is just going to simply move that graph up and down. It doesn't shift it left or right. It literally just moves it up and down. So this is the effect of adding a number on the outside of the x squared, which makes a parabola. Let's stop that slider. Now, let's investigate what happens if instead of adding the number on the outside, we add it to the inside. And just to make this a little cleaner, I'm going to clear off my old graphs. So I'm back to the basic y equals x squared graph. This time, I want to add something on the inside. So I'm using a parenthesis. So let's say I want to have a plus 2 on the inside of the square. So instead of adding the 2 on the outside of the square, I'm adding it to the inside using parentheses. Now, unfortunately, these are both green, so I'm going to change the color here and make it like orange. So you can see my new adjusted graph where I had a +2 on the inside is now orange, and my original graph is green. Notice my graph where the equation for which I had the 2 added on the inside, the graph has actually moved to the left. Instead of going up to or right to, it actually moves the graph left to. So what we have is an effect that is the opposite of the sign we see on the inside. Let's try another one. Let's say we have y equals, and instead of adding 2 on the inside, let's subtract 5. Look where that graph ended up. A -5 makes the graph go over to the right side of where it was originally, so that the vertex is at 5, 0. So adding something or subtracting something on the inside of the square appears to shift the graph left or right, but it goes the opposite direction of what you would expect from the sign. If it's a plus number or a positive number you're adding on the inside, you go to the left over here. If it is a negative number, you actually go in the positive direction or right. And once again, we could use a slider to show this in general. So I'll just say x plus h, I was anticipating the h there, squared. And I'll click the h to create a slider, and it starts me at x equals 1. I'm going to turn off these other ones so it's not so cluttered. And the black graph is the one I'm using with the slider. I can then hit play. And you notice for bigger positive values, you go to the left. For bigger negative values, you're going to the right. So adding something on the inside of the square for the parabola actually doesn't affect the width or where the graph is up and down. It purely affects where it is left or right, and in the opposite direction of the sign that you actually see directly in the equation. Through experimentation in Desmos, we saw that adding a constant on the outside shifts the graph vertically by k units up if k is positive and down if k is negative. So having a constant on the outside of the square shifts it up or down. Having a constant on the inside is going to shift it left or right, but it's going to be the opposite way we expect. And this is a key thing to remember. If h is positive, it's actually going to go left in the negative direction. So, and if h is negative, then it goes right in the positive direction. Okay, so it's the opposite direction you would expect. So again, shifts opposite direction. And that's an important thing to keep in mind. So anything on the inside is going to go the opposite direction. Whereas when you add something on the outside of the square, it basically mimics the sign you see. All right, so a couple of examples here. Let's say we have these 4 equations for the functions f, g, p, and w. Based on the equation, let's think about how the graph has been shifted. Starting with f, notice that the constant is added on the inside here. 3 is added on the inside of the square. So that's a left or right shift. It's a +3. So remember, +3 would be the opposite direction, so you would shift left in the negative direction. In the function g, the +1 is on the outside of the function, so that's an up or down movement, and the sign tells us exactly which direction to move. So because it's plus, we shift up 1 unit. The function p has 2 constants in with the square. It has a constant on the inside, this -5, and then a constant added or subtracted on the outside. Remember, subtraction is just addition of a negative. So what we have here, if we look at them one at a time, is the -5. Remember, inside opposite direction, so that's shifting right 5. And then the -2 on the outside, that means down 2. So there's two shifts in that graph. W of x has, again, two alterations. We've got a +4 that's added up before the square happens and a -5 after the square. So an inside and outside movement. +4 on the inside, think opposite direction, shift left, because left will be in the negative direction. Left 4 units. And then the -5 is on the outside, direct shift, minus means down 5 units. So these are shifting rules for parabolas. You're going to see these again in Math 111. In fact, we will in Math 111 look at this in general for how this works for not just parabolas, but for other types of graphs. Now, we can extend this and look at specific points in the graph of a parabola. In particular, the vertex is a hugely important point in the parabola. The graph of y equals x squared, remember, has a vertex at the origin. So if we think about how the vertex is being shifted just like the rest of the graph, we can actually shift that point and find where the vertex is of any function if it's written in that form of being able to see a constant added on the inside or a constant added on the outside. So if we look at this first function, this is the one we had in the last, all of these are the examples from the last page. We have x plus 3 quantity squared. The 3 is on the inside, so remember that means shift left 3. So if my origin point, 0, 0, got shifted left 3 units, I would be at a -3. So it's only the x value that's shifting, so my y value would stay at 0. So there's my vertex, -3, 0. My second graph, remember the +1 means it's on the outside, so it shifts up. That's only going to be shifting the y value because y is up. So we wouldn't change the x value from the origin. We'd stay at 0, and my y value would be 1. In the next function, we shifted with the -5 right 5, so that means my x value increases by 5, goes to the right 5, and my y value goes down 2, so that would be from 0 down 2 would be -2. So my vertex is 5, -2. And then in my last example here with specific numbers, we have a +4 inside the square, so that means +4 means go the other direction, so -4 from 0, and then the -5 on the outside, shift down 5, so from 0, shifting down 5 would be -5. So we can very easily, with the shifting ideas, actually shift that original vertex, which was at the origin. What we're after here is just a general rule. If you have a quadratic function written in this format where you see a constant inside the square and then a constant added on the outside, this is often referred to as vertex form. I am leaving one thing out, which I'll go over next, but this is, in essence, vertex form where the a is 1. And when you have this format, the vertex can always be easily seen. That's why it's called vertex form, by thinking about the shift from the origin. Notice instead of putting a +h here, I wrote a -h inside. That's because that's typical of how most books show it, because they want you to remember that the h, the sign you see there, is the opposite of the direction you're going to move. So often they'll show it with a minus to emphasize it. So when we think about it with the minus, then just HK would be the vertex because the sign change has already occurred by writing a minus there. So when you have an equation in vertex form, you know the vertex.